A little bit, 10 minutes.
Yeah, that's fine.
15 minutes.
So we'll be moving into the soft lithography, which is the making of the PDMS devices. One really nice website, if you want to look up anything else, is Make Simple Microfluidic Devices. And they go through a lot of detail on how PDMS micro devices, but also paper microfluidics that we'll be playing around with later this week. It provides really easy to understand instructions with our tea will come in 15 minutes or so. So we'll make a head start to make sure that we don't get called out with lunch.
Okay. I want to take water from a bottle to lay.
Hey. So this is a good website where it gives prices, where you can source different materials to do both PDMS. You should be able to get a copy. You should get a copy of the slides with the course. I've given
Yeah.
copy, so all the slides should be available at some point.
They'll be giving at the end.
Okay.
I just want to go through few of the things after
Now.
the day gets over, so I would just
Yeah.
note down the things and then try to go through. Slides are सब मिलेगा सारा presentation and
So soft lithography is the use of the mask that we've, or the template that we've made by photolithography. So here we've got a silicon wafer. We've done our photolithography. We've got bits of our photoresist left. And we've got other areas where our photoresist has been removed. If this was a negative tone photoresist, this would have been the, need to get it right now, negative photoresist, cross links. So this would been exposed, this would be have been a non-exposed area. What happens is that you then pour a two mixture polymerization that I'll give the details of later. It's a highly viscous liquid. You pour that over the substrate, allow it to cure in the oven, and it's a flexible polymer, so it then can be peeled off. And one of the nice things is that it actually is flexible, so it can move around a little bit. This slide here very much clarifies the topic that we just were talking with. Where does the design come from? And the design of the device that you're going to make sits in the photomask. And the photomask, you could make a very simple drawing in a package like PowerPoint, but mostly you'd use CAD-based software to design your file, and then a photomask can be made either using a commercial printer, or if you've got a very good print facility at your university, a high quality laser printer may also already do the job.
kindly go slow.
So the photomask, as you can see here, it's mainly opaque. The light will only go through the transparent areas where it will expose those areas of the photoresist, which after the development, the exposed photoresist is better cross-linked and therefore will remain on the substrate, whereas all of the other material is washed away. So we have our full plate here coated with photoresist. We only expose a cross structure, two crossing lines with little circles to be able to make easy reservoirs. We only expose those areas. They will cross-link. During the development process, all the other photoresist washes away, and we're left with these structures sitting on top of our wafers. And if the package comes in from DHL today, I have a couple of wafers there, and you can actually, with your finger, you can just feel the structures sitting on there. What we then do is that we cast the pre-polymer mixture over it. We can peel the polymer off and then stick it to another flat substrate where the ridge that was present on this template will end up being a little groove in our PDMS because it's cast over it. If we seal that to a flat substrate, we've got a microchannel left.
What is PDMS?
That's the material. So polydimethyl siloxane.
Okay.
I've got the structure here. So this is the structure. So it is the same material they use to insulate electronics.
Yeah.
It is also the same material they use for silicone implants. It is the same material you use for siliconing in the bathroom. So it is the squashy material for caulking in the bathrooms, that's silicone as well. So it is that squashy polymer material. The one that works really well for microfluidics is called Silgard 184. Sold by Dow Corning, the whole world is using it. They must have a right pre-polymer length or something. So you buy Silgard 184. There's a whole range of different places where you can buy them. You mix it in a 1:10 ratio, pour it over your template, and then you can peel it off after you've cured it for about an hour at 80 degrees, or you can also do it 2 hours at 60 degrees. There's a range of different processes.
1:10 ratio of what? One is this.
So you take 10 parts of the base polymer, 1 part of the of the catalyst. And the whole process should be playing on this movie. Did I put it there yesterday? And yesterday it played. Let's see if it wants to play. There we go.
Today we're going to show you how to make a PDMS microfluidic device. PDMS is a cross-linked polymer that is poured over a mold to make channels, microfluidic channels, in your device. This is an example of a final PDMS chip. And this is an example of the laser cut mold that was used to make this chip. You can make molds out of a variety of different materials. As I mentioned, this one was laser cut. You can also 3D print your mold.
So a mold is
Or you can
anything
use
that's
a combination of
got a
materials,
positive structure on there that you
such
can
as this
pass.
one, which is a push button device, which is made from laser cut acrylic sheets and double-sided stick tape.
All right, to get started
Very
with
simple
making our
cooking chemistry.
PDMS-based
That's why I
device,
introduced this
first we're
movie.
going to take a weigh boat, put that on the scale. With the weigh boat on, we're going to tare, or you can press 0. Basically, we want to weigh out the appropriate amount of elastomer or PDMS based on the weight. And so the ratio that we want to use is a 10-to-1 ratio. So I'm going to start off pouring the base, the PDMS base, and I'll pour 30 grams. When you're pouring this PDMS base is a very viscous liquid. So you can see it's going to come out kind of more with the consistency of honey. And then as the numbers go up, I'm going to kind of watch it as it gets close to 30 grams. A little bit more. Oop. Now we're going to go a little high. But then what I'm going to do to kind of keep my mess contained, you can see I'm twisting the bottle.
It is very sticky. It's very painful to
And I
clean
got
up.
a little bit of PDMS on the lip that I'll then just wipe off with a chem wipe. Dispose of that in the regular trash. Okay, so I was a little bit high on the amount, but like being a little bit off is okay. So the next one I'm going to do is tare. And then I'm
It doesn't play in presentation mode. There we go.
Today we're going to show you how to make a PDMS microfluidic device. PDMS is a cross-linked polymer that is poured over a mold to make channels, microfluidic channels, in your device. This is an example of
That's where we got to.
here. In comparison to the base, the PDMS base, the curing agent is less viscous, so it's more the consistency of water. So instead of pouring, I'm actually going to use a transfer pipette. And we want to measure out 3 grams.
So 1:10 ratio, about 30 of one, about 3 of the other.
Yeah. again. So
No,
you can
this
see
is
that went up
the,
pretty fast,
the
so we'll go
catalyst. So
a little bit
there
less
were
on
the 2 bottles.
next amount.
So this is the second reagent.
Okay, one more. Okay, so a little bit high, but again, that's okay. You're not exactly at 30 and 3. Alright, so then the next step, I'm going to take, we've got our PDMS base and curing agent. So I'm going to take this off the balance and then rigorously mix.
And mix.
Now we're going to mix our base and curing agent together. So mix somewhat rigorously, but also for at least a minute or two. Basically, the goal is to make sure that these 2 components are mixed very well, otherwise we'll have problems later in our manufacturing.
It's very viscous, so mixing is hard.
Alright. That looks pretty well mixed, so again, stop our mixing. When you're picking up your spatula so you don't drip everywhere, I recommend kind of spinning it around and holding it over a hem wipe on your way, or some kind of disposable items on your way to the trash can. Alright, now that we've mixed these 2 components together, you can see there's a lot of bubbles that form during the mixing process. So what we're going to do next is put this into a vacuum chamber and use that suction to help pop and get rid of all of these bubbles. Here's the vacuum chamber we'll be using to degas our PDMS today. So you can see I've put an aluminum foil lining. This is just to contain any mess in case your PDMS spills.
You only clean up
So I'm gonna
PDMS
put
once, and then you're
our
very
wafer
careful
bar
keeping your lab
boat
clean because it
inside
sticks
of
to
the
everything.
chamber. Close the lid, and then we already have our vacuum turned on. So just make sure you find the right tubing. So you can turn the vacuums on, find the right tubing, and connect it to your vacuum chamber. And then at this part, we're going to turn the valve such that we're pulling vacuum from only the chamber. And then we let this set for about 10 to 15 minutes until the bubbles are gone. Alright, so the next step before we pour our degas PDMS is to actually prepare something to pour it into. So for this type of master mold, which is has a laser cut double-sided tape to form our channel features, I'm going to actually put a piece of aluminum foil that I've molded into the shape of a petri dish within the dish. Make sure there are no tears in the foil around the creases, and also that the foil is about as flat as you can make it in the center of the dish to minimize leaks and also minimize PDMS that might run under your master mold. If you're concerned about a non-level surface, you can also tape your mold to the foil, which I won't do this time, but that is an option in later fabrication.
The aluminium foil makes the getting device out later easier.
The foil. So next we're going to pour our degas PDMS on top. Alright, so in order to remove our degas PDMS, I will not just take things apart because that will cause the PDMS to splash. First what I'll do is I'll actually turn off the vacuum. So that's off. And then the next step, I'm going to close the valve so that way the in between the chamber and the outside is closed off. So now I've changed the valve and then I removed the tubing. And then next what I'll do, go and take off this red cap. That's optional. We could also evacuate through the other hole. And I'll very slowly turn this knob to allow air back into our vacuum chamber.
If you do it too fast, it becomes a mess and it's cleaning up again. So it's all minimizing your cleaning up.
Alright, and then once it's fully evacuated, you should be able to easily lift off the top of the lid. Alright, so now you can see there's still a few air bubbles within the mixture, but this is an acceptable amount. Compared to before we put this in the vacuum chamber, there was a lot of air bubbles, so we successfully degassed our PDMS.
If it wouldn't be acceptable, just put it on the vacuum for another 20 minutes.
Degassed our PDMS,
Go and have a coffee, come back.
We'll take our boat and then our liquid boat and pour it into the features. Since we degas it in a separate container from our master, to try to avoid introducing air bubbles, we'll pour slowly and also close to the surface. And I like to just pour over the center of my master mold. Then as an added tip, if you want to get more of the PDMS out of your boat, you can actually take one of these spatulas and scoop it out, depending how thick you want your final PDMS device to be.
If you've done some cooking with honey, it is very similar.
And then last but not least, we'll just put this in the oven between 55 to 65 degrees Celsius for about 2 hours. If you have a 3D printed mold, check the temperature limits of that 3D printed plastic because you may have to use a lower temperature.
If you need to decrease your temperature,
Next,
you
we're
need to go
going
for
to
longer.
show you how to use plasma to bond this PDMS, already complete PDMS chip to a glass slide. And we'll do that by first cleaning the PDMS and the glass, baking the glass for about 5 minutes at 100 degrees Celsius, and then applying a plasma treatment for 60 seconds, bonding the two pieces together and putting them in a 90 degrees Celsius oven. Okay, so to clean the
I think we can stop there because we haven't touched on bonding yet here, but that, I think, gives a nice visual of how simple it is to make PDMS devices once you've got a template. It's all in order again. So PDMS as a material is really good because it has a Young's modulus of 1 megapascal, should have been a capital P there, whereas most polymers are a lot harder. They are about 1 gigapascal. So PDMS, it's really squashy. If you know the caulking in your bathroom, the squashy material that you put around the sink to prevent water from ending behind your wall, it is that level of squashiness. And again, I hope that the devices come in today so you can actually have a feel of them. It confirms over a large area, and so-called hard PDMS, so PDMS where you, instead of using the 10:1 ratio, you've used a little bit more of the crosslinker compared to the polymer base. It becomes a little bit stiffer, but it then becomes really good at replicating nanometer-sized features. It is transparent also in UV, so compared to some other plastic materials. If you want to use some UV fluorescence, PDMS is still great. It's chemically inert, so there's a lot of solvents that it is compatible with. It's got a very low surface energy, and you can bind it reversibly to most flat substrates, PMMA, COC, glass, silicon. You just take it off your mold, you stick it on, and you've got a watertight seal, so you can fill your channels with water and the seal won't break. If you want to apply some pneumatic pressure, you may want to activate the surface as she was going to do in the movie over there. You put it, expose it to an oxygen plasma, which is the purple-like fourth state of matter. That activates the surface and allows you to irreversibly stick your PDMS to glass, and that means that you can apply a lot higher pressure before the device tears away from the substrate again. It's a durable material, can be easily cleaned and reused. It's got very low thermal expansion, so if you want to do PCR, it doesn't shrink or expand a lot when you're doing thermocycling. It's biocompatible. It is used sometimes as a food additive. It's used in food packaging. It is used in implants, so it is safe to use, and it's also environmentally benign. So you can just the waste, you can just put it in the bin. And after fabrication, because it's so flexible, you can just peel it off the substrate, and it can replicate nanometer size features. So here you can see a substrate that was made using nanolithography, and you can see that the small features, submicron features, are very nicely replicated into the PDMS structure. which again becomes important if you want to grow cells on a chip, because sometimes cells like to have a micro or nano structured surface. Cells don't really like something flat. You can use the replication ability of PDMS in order to create these devices. Then a little bit more detail about where the lady was going into the movie. How do we bond PDMS? PDMS chemically, it's a polymer, but it is close to glass. And if we put it under a plasma, we can, for the loss of water, we can chemically covalently bind the PDMS to either another slab of PDMS, or we can use, as the other side, we can use glass. And that way we get a chemical covalent bond being formed between our microfluidic structure and the cover plate, which means that we get very strong bonding. So it is understood chemistry. We can activate the surface using a plasma. It removes the organics, it activates the surfaces, and then we get a chemical bond being formed. What the plasma treatment also does is that it changes the contact angle. So native PDMS is hydrophobic, so water will bead up. But if you treat it with a plasma, if you activate those oxides into hydroxide groups by opening them up, we can actually get a lot more hydrophilic substrate with a very low contact angle. The challenge for the use of the devices, however, is that we have what you call hydrophobic recovery, which means that the polymer chains, they rearrange and we get back from our hydroxylated surface to having our silicone material again, which is hydrophobic. So over a few hours, we are back with the hydrophobicity where we started, unless we chemically covalently link. In this case, HEMA was grafted to the hydroxide groups. At that point, the hydrophobic recovery is not as effective, and we can continue to work with a hydrophilic substrate. This also puts a challenge on working with PDMS, because if you've got it hydrophilic after plasma treatment, your surface chemistry may change due to this hydrophobic recovery. And that could be problematic. Okay, I think after this one is a good point. So if we do droplet microfluidics, we have a continuous phase is typically the solvent that is wetting our microfluidic device, and the dispersed phase, the one that's making the droplets, is the one that is not like the chip material. So if we've got a hydrophobic chip, then our continuous phase will be the oil and our droplets will be aqueous. If we've got a hydrophilic device, then our continuous phase will be the water and our droplets will be the oil phase. If we have a PDMS droplet system with hydrophobic recovery, we may see a phase inversion where water and oil swap who is continuous and who is dispersed phase as the surface chemistry changes. So from that perspective, doing only a plasma treatment and not covalently changing the surface chemistry is a dangerous thing to do for droplet microfluidics, because you may change the identity of your dispersed and your continuous phase. At the same time, the hydrophobic discovery comes with a change in surface charge. We've learned from Professor Baga, surface charge is the driver of electroosmotic flow, which means that during the hydrophobic recovery process, our EOF will be unreliable. Our EOF will slow down and slow down and slow down because our density of anionic charge on the surface decreases. Again, something to keep in mind, oxygen treatment is really good to get the bonding. If you want to use your devices but want to have stable surface charge, you may just want to put them on the shelf for 2 days till the hydrophobic recovery is complete. Or you may want to surface modify your PDMS so that you're not reliant anymore on the surface charge. After tea, I will be talking about different ways that we can use the flexibility, the air permeability, and the qualities of PDMS as a sorbent in more detail. But we've got tea now. So let's take a little break and then we go have a cup of tea and then we'll continue on the journey.